Well, here's Truss Lab Part 1. The meter stick is horizontal. Here's Truss Lab Part 2. The meter stick is at a diagonal and the string is pulling up at a diagonal. And here's Truss Lab Part 3. Now the top string is coming down at an angle. Now can you tell I swapped out the green spring scale for the red one? The forces are way bigger. The angles have to be measured up there at the top. You do not have to build this. Just follow the problem I do on the board. So here's the problem for Truss Lab Part 3. We're going to have an angle of 20 degrees, an angle of 30 degrees. The weight is still 1.8 newtons plus half the weight of the meter stick. And that's what's going down on this side. Since strings can only pull, what do you think it's doing to the binder clip? Well, it's got to pull this way. So if we have FW going down and FS pulling at an angle, what do you think the meter stick is doing to the binder clip to keep it from moving? Yeah, that meter stick is pushing that binder clip out and up. Getting rid of all the equipment, we now have the tail-to-tail free body diagram. Let's solve for the force of the spring scale the easy way. We'll put the vectors tip to tail. First, I'll draw the weight. Well, how long do I make this line? The force of the scale has to pull down to come back to the start of the problem. It can't do it from here. The only way to make that force of the scale pull down is to make the force of the meter stick push all the way up to here. Now the force of the scale can complete the diagram going back to the origin to show that they all add up to 0. But what's that angle up here? Well, this is the angle between the scale and the meter stick. Well, that's what I have right here. This dotted line was the meter stick. So it's going to be 20 degrees. Well, if that's 20 degrees and that's 30 degrees, I automatically know that angle. And since I know what the weight is, I can now use the law of sines to find both of these. That's the one I'm looking for. And we get a force of the scale of 3.0 newtons. Now, in my actual apparatus, those were not the angles. I only did this as an example. In the experiment that I was showing, those angles produced a much larger force. So be careful if you do this at home. Don't break the spring scale. Swap it out and use the red one to be safe. Well, we did the law of sines. What can we say about the components? We can see that the meter stick pushing this way has an X component and a Y component. And the scale pulling this way has an X component and a Y component. Well, does anybody see anything different now about these components? In this setup, the scale is now pulling with a Y component that's going down. So what's really holding up the weight in this case? It's the Y component of the meter stick. The Y component of the scale or the rope, that's not helping. That's actually pulling down. That's what makes this thing so much bigger. How about the X components? Hey, they still have to cancel out. This weight, it doesn't go moving sideways. The X component this way and the X component that way, they have to be equal to each other. This Y component going up is now equal to this Y component going down plus the weight going down. You need more help? Read the chapter notes. Everything I'm doing on these videos is spelled out in those chapter notes with examples worked out. Beautiful diagrams, better than these diagrams, that's for sure.